now we have a unique presentation, something that was just briefly mentioned on this Congress that has to do with artificial intelligence, helping us or helping the laboratories studying and analyzing huge amounts of data for origin determination. And we will have on the stage the lovely Zainab Ali from Danat, from the Bahrain Institute of Pearls and Gemstones, which has a very well-equipped laboratory. And she's a gemmologist. She's a actually, she's a chemist, but she has a degree in gemmology, and she not only contributes to gem testing, but also to research at Danat. So everyone, please give a big warm applause for Zainab Ali. The stage is yours. That's your microphone.
Thank you, Roy, for such a wonderful presentation. So, do you hear me well? Okay. Good morning, everyone. So I'm Zainab Ali, and as Roy said, I'm a gemmologist and a chemist at Bahrain Institute for Pearls and Gemstones, Danat. I would like to begin first by thanking the ICA for such a wonderful Congress. And I'd also like to thank my fellow speakers for all the knowledge they've shared, for all the heartwarming, wonderful stories they've shared as well. And although I'll be shifting the environment into something more scientific, hopefully it would be as interesting and also as informative. So, as you all know, Danat offers three main services. The first one being producing certificates for pearls, gemstones, and diamonds by the laboratory department. We also give so many gemmological courses regarding pearls, gemstones, and diamond in our education department, and we also conduct many gemmological, scientific, and environmental research in our research department. And the presentation that I'm about to give for you today is the result of one of these studies that we've conducted. So my presentation will be titled The Application of Machine Learning on the Chemical Analysis of Gems, and this would be a case study on emeralds. Gemmologists have been longing for the longest time to find a way to determine the origin for gemstones like sapphires, rubies, emeralds, pearls, and the main reason behind it is that the origin of these gemstones can drastically affect their value. So before the introduction of any advanced instrumentations, we only had the micro world of these gemstones if it was accessible, of course. So by the power of magnification and seeing some characteristic inclusions, we were able to determine the origin of some gemstones. However, as the technology evolved, many spectroscopic instrumentations have been introduced to the gemmological laboratories and used to aid the origin determination, as well as the use of chemical analysis that might be conducted using many various instrumentations. And of course, we're here trying to introduce new technologies for the origin determination of gems. So we can say that gemmologists left absolutely or spared no effort into finding any way, any clue to determine the origin with the highest accuracy for gemstones. And this is what we have been doing in Danat. So in 2019, we've published an article that is titled Emeralds from the Most Important Occurrences, Chemical and Spectroscopic Data in Minerals. And in that article, we've used various spectroscopic instruments like the FTIR, the UV-Vis, the Raman, the photoluminescence, and we've tried to distinguish between the different occurrences of emeralds. We've also used the chemical analysis that was conducted using the laser ablation-inductively coupled plasma mass spectrometry, or the LA-ICP-MS, and using that data, the binary plots gave us very promising separation between those different origins. So what I'm about to present for you today is a follow-up study that we've conducted to use the ICP-MS data, which is considered as quite large data, and to use the machine learning and artificial intelligence, specifically the tree classifier methods, to hopefully find a method that might predict the origin of gemstones to help us gemmologists having higher accuracy for origin determination. So this study includes three main phases. The first phase was the collection of samples from different occurrences around the world, or the most important occurrences. The second phase was the conduction or the acquisition of data using the ICP-MS, and the third one, of course, was the machine learning. I'll go through each one of these phases and explain what Danat has done through each phase of them. So, the first phase, as I've said, was acquiring or having the samples, which was done by our field gemmologists, either from the mines themselves or from very reliable sources. And you can see that the occurrences that we're talking about here are 9 occurrences, including Colombia, Brazil, Madagascar, Zimbabwe, Zambia, Ethiopia, Pakistan, Afghanistan, and Russia. And in the following slide, you'll see a table that includes a brief description over these samples. So we had a total of 71 samples with carat or weight ranging from 0.04 to 2.5 carats, and the colors of these samples were ranging from light green to dark green. So that was the end of phase 1. We've collected the samples, and now we went for the ICP-MS to acquire the data. So there are a few important points about the acquisition of data using the ICP-MS. The first thing is that the chemical analysis was done over areas of the samples that were mostly homogeneous in color and clear from inclusions. The reason behind that is we didn't want the chemistry of those inclusions to interrupt with the chemistry of the emeralds, which is the main scope of the study. The second point was that 3 spots have been taken from the majority of samples, except for those from Zimbabwe and Ethiopia. We've taken 5 spots for these samples since we had fewer number of samples from those 2 occurrences. And finally, all the values that were below detection limit and below quantification limits were replaced with 0 since they're not really considered as real values. And that's the end of phase 2 of the acquisition of the LA-ICP-MS data. So now let's move to the exciting part. Not that the first 2 parts were not exciting, however, this is the part where we might see results or not. So the machine learning process also included many steps. Now, the first thing that we've done is that we've excluded the coloring chemical elements, which are the chromium, iron, vanadium, because using those elements in classification would only help us classify emeralds according to their color rather than according to their origin. So these were excluded. Now, the second point, we've took 20% of the data to be used later on as a prediction set to test the accuracy and reliability of the methods. And of course, each spot of the samples was considered as one sample in the softwares that we've used. And a correlation test was conducted, which I'll talk about more in a minute, using the SPSS software. And then the 3 classifiers methods have been conducted using the WACA software. And finally, the 20% prediction set that we've excluded at the beginning was finally used to test the accuracy of those methods. So now let's see what correlation tests have done, or why have we actually conducted a correlation test at the beginning. So doing a correlation test before starting with any statistical method is very important because we need to understand the correlation between those elements. Now, we're using, of course, the 3 classifier methods because you can see the outcome of the tree. You can actually see the classification, and we can determine what went wrong. However, if you're using such classification and you're putting very correlated or highly correlated elements, this would disrupt the whole tree. So we need to understand the correlation so we can end up with the correct combination of elements. So from our previous study, we've concluded that these 12 elements before you in this table are the ones that are mostly useful for separation of emeralds occurrences. And we've seen, using the correlation coefficient, that the 4 most correlated elements were first the pair of magnesium and sodium that had a correlation coefficient of 0.94. So as the correlation coefficient goes up to 1, that means that they're highly correlated, whether, of course, directly or positively or inversely. And as it goes to 0, that means there's no correlation. The second highly correlated pair of elements were the rubidium and potassium that had 0.862 correlation. Now, I know the table is too small, so just to make it clearer, we have these 12 elements, and the two pairs that are mostly correlated are the sodium, magnesium, and then we have rubidium and potassium. So what does this help us with? Understanding this correlation means that we can never use sodium and magnesium within the same combination, and we cannot also use rubidium and potassium as well, because they would disrupt the tree. So any combination of chemicals using these 12 chemical elements, we have to exclude one chemical element of each of those two pairs. And if you would think about it, this would leave us with 4 different combinations. And the combinations are as shown. So we have the first combination with sodium and potassium removed, the second with magnesium and potassium removed, the third with sodium and rubidium removed, and the last one with magnesium and rubidium removed. So for each decision tree, for each method that we would use for classification, we have to test these 4 different combinations and see which one gives us the best prediction out of the prediction set. Now moving on to using or to deciding which decision trees are we going to use. So for any of you who had used the Weka software or the statistical methods, there are plenty and plenty of methods even within the decision tree area. We've only chosen 4 different methods to concentrate on because these 4 were the only ones that gave us 0% error, and they gave us a kappa statistics value of 1. And as you can see in the table, that as of course the kappa statistics goes to 0 and below, that means it's a very bad, and of course this is an expression of the reliability of the method. So as the kappa statistics increases, that means that you can be more reliable over these methods. And these were the only 4 that gave us 1 kappa statistics, which is of course quite extraordinary value. So the 4 methods were the Spark method, the best first, the random tree, and the J48. And now I'll go through each one of those methods, and we'll see, using the prediction set, how many samples were predicted correctly and what went wrong if the percentage was very low. So the first method here is the Spark decision tree, and you can see that for all 4 combinations, the percentage of the samples that were correctly predicted were 84.4%. which is, to be honest, quite decent percentage. However, as gemmologists in a laboratory, we don't want to leave any room for error. So we want to achieve something that is much higher. In order for us to do that and to develop the method, we need to understand what exactly went wrong. So when looking at the tree, we can see that the classification here started with cesium being less than, more than, or equal to 162.5 ppm. And this is actually where the problem started, right at the head of the classification. So this value of cesium lies between the ranges of the emerald samples from both Madagascar and Pakistan. So before even going to the prediction, we already know, looking at the tree, that the samples from Pakistan and also from Madagascar will not be predicted correctly. So let's look now at a sample of the prediction set and see how were they predicted using this method. Okay, so this is the table, and you can see that the Zambian emeralds have been correctly predicted as Zambian. However, the ones from Pakistan have been falsely predicted as samples from Afghanistan, and also the Madagascar samples have been falsely predicted as ones from Afghanistan as well. So, as we've already anticipated, this method will not be very good into the determination of Pakistani and Madagascar emeralds. So let's move now to the second method, and hopefully we'll have better results and better percentages. But of course, one can only hope. It wasn't better at all. This was actually the worst method out of the 4 ones. So you can see that with the combinations where the potassium was removed, the percentage of the correctly predicted samples were 24.1%, whilst when the rubidium was removed, it was even down to 11.1%. So to look at the tree and to see what went wrong exactly with this one as well, we see that the classification also started with cesium being less than, more than, or equal to 162.5 ppm. However, the problems did not stop there within this tree, because along the tree, that was only the first problem, but along the tree there were so many chemical elements that had a value that lies between the ranges of two different occurrences of emeralds. And of course, this was sensibly the worst method because of the many mistakes within it. And you can see here in the production set that the majority and many samples, like the Pakistani samples, were falsely protected as Pakistan, as Afghanistan and Madagascar, sorry. And the ones from Colombia were falsely protected as Afghanistan, and the list goes on with the false protections. Actually, the majority of samples were falsely protected in this method. So the third method, which is the random tree, gave us a different percentage for each different combination. The first combination gave us 84.4%, the second 80%, and the third one with sodium and rubidium removed gave us 97.8%, which is incredibly high and very, very promising result. And of course, the fourth combination gave us 15.6% correctly protected samples. Now let's forget about the three combinations and focus on the one that gave us the highest correctly protected samples, which is the combination with the sodium and rubidium removed. So when we take a look at the tree, we can see here that the classification has started with lithium rather than cesium. And in this case, the lithium started with it being less than, more than, or equal to 207.5 ppm. So for now, we know that starting the classification of the occurrences with lithium is giving very promising and very positive results. However, 97.8, although it's very good, it's still not quite what we want to achieve. We want even more. So this was the prediction for this method. And you can see that mostly all samples were correctly predicted, except for one from Brazil that was falsely predicted as one from Madagascar. Moving on to the last and fourth method, hoping that we would find something more than 97.8%. And to our surprise, we had 100% correctly predicted samples from the J48 method with the combinations of the rubidium removed. The sodium removed, of course, or the potassium removed gave us 15.6%. However, the other combinations, the two with the rubidium removed, gave us 100% prediction. And once we take a look at the tree, we can see that this tree and this classification also started with lithium being either more than, less than, or equal to 163 ppm. And of course, it always predicted the samples correctly. So this actually agrees with our previous study that I've mentioned at the beginning of this presentation. So in our previous study, we have concluded, using only the ICP-MS data and the separation between the binary plots, that we can differentiate the emeralds occurrences using the lithium content into low lithium content, which is below 200 ppm, and medium to high lithium content that is more than 250 ppm. So the ones with low lithium in the previous study was Afghanistan, Colombia, Madagascar, and Zambia, and Brazil, sorry. And the medium to high lithium were the ones from Ethiopia, Russia, Zambia, and Zimbabwe. Pakistan was not included in the previous study, however, it is included in the present one. And of course, our findings of having the best method starting the classification with lithium quite agrees with the ones or with the previous studies that we've conducted over emeralds. And this is the prediction table, and you can see that every single sample has been predicted correctly, whether from Zambia, Russia, Pakistan, Colombia, and you can name it out of these 9 different occurrences. So to conclude, I'd like to say that machine learning is an incredibly promising and exciting technique and technology to be used in the origin determination of gemstones. And we at Danat are thriving to even have more samples from different occurrences, from different mines, and also to expand our database and to take more ICP-MS data and of course use them in these methods and developing these methods until reaching a method that is very highly accurate and that might aid the origin determination for us. The ICA this year is talking about future. Artificial intelligence is the future, and hopefully we'll be able to implement it in our gemmological laboratories. Thank you all so much.
Thank you, Zainab. Don't leave the stage. What a brilliant presentation. Thank you very much. And I'm sure that you must have a couple of, we still have some minutes for a Q&A. Is there, yes, Warren. Thank you.
Tess, I would like to donate samples from Rock Creek.
Oh, that would be wonderful. Thank you so much. Hopefully it wasn't too scientific or too boring.
Guillermo.
Thank you for such an amazing research. I feel we be developing some different approach to try to understand locations, and we have some research done in our laboratory. So we would like to share whatever we can do. We do it more with the chromophores. So, but I feel the same thing. I would like to be able to give you more samples from every single mine in Colombia and see if we can work out to get more, whatever we did, share with you so we can see more data and we can see more elements. I'm amazed for these results. Thank you.
Oh, absolutely. Thank you so much.
Do we have in the room any other miner or mining organization that wishes to follow the trend? Yes? I'm kidding. Nobody raised a hand, unfortunately. So thank you very much, Zainab. It was a brilliant presentation. Oh, my voice. It was a brilliant presentation.
Oh, don't worry. It's
yeah,
good.
I know.